Excellent. Well, thank you for this opportunity to present some ongoing results of a project. The peer project is entitled a system level study to evaluate the role of soil gradation on seismically induced embankment deformations. The test in particular that was funded by peer that I'm going to show results of, along with some prior work, was performed by Nathan Love and Jacob Stracilla, two graduate students at UC Davis. Trevor Carey, formerly a postdoc at UC Davis, now a professor at UBC. And then myself and my colleagues at UC Davis, Katerina and Alejandro. And so the motivation underlying our work really is gravelly soils. And gravelly soils are challenging for many reasons. And I think a large part of that has to do with semantics. And so if I say gravelly soils, you might think of that condition, or perhaps a soil like that, or a soil like that, or any of these other types of materials. And so there's a whole wide range of materials that are quote unquote gravelly soils. So more specifically, what is our motivation and what are we interested in? In industry, we differentiate gravels from sands, even though both liquefy, which may infer or impress upon us that gravels are distinct and unique and should be handled differently in some ways. Yet it turns out that the cutoff between sand size and gravel size is arbitrary and varies around the world. And more fundamentally, both of these smaller and larger size particles are controlled by frictional interactions between the particles themselves. And so our research for this project and for the NSF project that it's linked to is really driven by the hypothesis that differences between gravels and sands is primarily rooted in the differences in particle size and, more importantly, perhaps the breadth of the soil gradation. And so this leads to, for example, this could lead to an increase in gradation from the perspective of poorly graded sand, which is our industry's benchmark, if you will. And we'd hypothesize that if that CU increases, we'd have a tighter particle packing and lower void ratio, which is an index change. We'd have an increased particle interlocking, stronger dilation, and higher stiffness, which reveals itself at the element behavior level. This would map to an increase in penetration resistance. It would also result in increased resistance to pore pressure generation and liquefaction triggering, but it would also result to a more rapid dissipation of excess pore pressures. And you'd have increased resistance to straining and reduced deformations. And that's ultimately what this project has an eye on, is trying to get to a predictive capabilities of field performance and field deformations. And so our long-term goal is to explicitly incorporate the effects of soil gradation and in both the characterization and engineering analysis of coarse grain soils more holistically. And so the research program that peer is funding is really strongly leveraging an NSF grant that's supporting laboratory, numerical, and some centrifuge work. The peer scope is to extend the centrifuge testing program to broader gradations, that is a broader range of CU values beyond those funded by NSF, while still leveraging all the developed tools, skills, and expertise that have been developed more recently. And so what this looks like kind of in a schematic view is that we're taking and varying the gradation of coarse grain soils as well as the D50. We're employing a number of different research methods, from laboratory, track, seal, and DSS tests, discrete element modeling, cone penetration, and then of interest today is the centrifuge testing or modeling on the bottom there. We're evaluating how that affects monotonic behavior, cyclic behavior, and penetration resistance. And ultimately, we're interested in the engineering system response. We want to really try to understand two things more accurately. One is this phenomena of triggering, and really that even necessitates a reevaluation or a revisiting of what we mean by a triggering criteria. And secondly is being able to predict deformations. And so in the next few minutes, we're going to take a look at these few boxes here highlighted in blue. So we're just going to jump straight into the test design, show you some details of that, and then go heavy into quite a bit of data, and I'll try to highlight a few of the main points. So we're going to first of all take a look at 4 different soils. All of these are have various gradations, and you can see the CUs varying there. If we put the gradation curves together, you can see the 100A material is our conventional poorly graded soil, which is kind of the most prevalent soil in our liquefaction triggering database. And then we simply have kept the D10 about the same, and we've laid the curve down so it becomes more and more coarse. And in the process of doing that, we've increased the coefficient of uniformity from about 1.7 to about 12.4. What importantly with that, what happens is that as you increase the gradation, the packing efficiency increases, and therefore the possible range of void ratio decreases substantially. So if we just focus today on comparing the blue of 100A material with the gray of 12Cu material, you can see that the entire possible void ratios for the 12Cu, that is Cu of 12 material, is substantially lower than even the minimum possible void ratio or maximum density for the poorly graded soil. So that's the first significant difference. And then the centrifuge model is using the 9-meter centrifuge at UC Davis, 40 times gravity and 40 times scaling of the viscosity to capture diffusion appropriately. We're using a rigid container with side-by-side models in parallel with each other, so there is no directionality dependence. Divided by an aluminum wall, a clear sidewall that allows recording of movement, and we have 2 different sensor arrays. Everything, again, is nominally placed at 40% relative density. And in schematic view, you can see that here, there's 2 different identical models. It's separated by an aluminum wall, and in side view, you can see that we have 1 array of sensors up on the upper slope, on the level ground, but somewhat influenced by the slope adjacent to it, a 10-degree slope, and we have another set of arrays mid slope down there. In photo, it looks like the following. You can see at the end of the test, the 2 slopes side by side, textured with some paint to monitor deformations and some red sand lines. You can see in the sidewall these black sand colored columns, which were placed adjacent to the sidewall to allow tracking with the high-speed camera system. And you can see that high-speed camera system down in the bottom left image. And you can see some of those columns as well as reference markers placed in the zone above it. And so in the model characteristics, we pushed 10 millimeter diameter cones before and after shaking and at various points in time. We're able to reevaluate the relative density that was targeted relative to what was achieved using a series of correlations we developed in previous work. And we have embedded shear wave velocities that we can track also. The combination of a lower void ratio or increased density and an increased shear wave velocity means that the shear modulus increases pretty substantially as the coefficient uniformity increases. And so the modulus of the system, the stiffness of the system comes into play during pore pressure generation, in particular during dissipation. You can see the CPT profiles on the right-hand side. The input motions for this is a 1 Hertz sine wave. It has 3 different phases to it. It has a linear ramp, multiple cycles at the target PGA, and then an exponential decay to allow the different soils to dissipate pore pressures at a rate dependent on the shaking magnitude. 5 shaking events, 3 different motions that were varied in the shaping to some extent, and you can see those on the right-hand side. The early shakes had a couple cycles of linear increase, a couple cycles of hold, and an exponential decay. The image that we're interested in is in the bottom right, and that happens to be the 3rd shaking event of these different tests. So that's a PGA of about 0.23 and an areas intensity of about 1.4 or so. And this is the motion. So you're going to see the same coloring in the subsequent, where you have a linear increase, you have a constant hold at an amplitude, and you have an exponential decay, allowing dissipations to occur gradually. So let's get into system performance for the next several slides. Everything you're going to see has only really focused on the top 2 or 3 accelerometers and pore pressure transducers on the upper slope and also in the mid slope. They are colored accordingly to the orange and to the blue, so you can track that as we go throughout. And we'll briefly take a look at the acceleration traces and the response spectra computed from that, the pore pressure generation and dissipation, and then the dynamic deformations from calculated acceleration recordings and permanent deformations from the PIV displacement. And we're going to focus on shake 3, as I highlighted previously. So we're going to first begin in just the upper left. This is the poorly graded soil, and we're going to begin with this one because this is our benchmark knowledge. And you can see, first of all, that in terms of the accelerations die away within the first 2 cycles. And this is the classic kind of exhibition of a fully liquefied case in the upper accelerometer, and even in the second level, it's also essentially liquefied throughout the shaking process. That's on the level ground condition. On the upslope condition, there is some indications that we have some dilation spikes that exist there. And if we now fill it out with the rest of the materials, the 33 ABC is slightly more well graded. Then the 25 ABCD is more well graded. And finally, the 12 CU is the most well graded of the soils we tested and the one that was added for the peer project. So we most efficiently can contrast the upper left with the bottom right. And a few things are noticeable immediately. First of all, the acceleration spikes exist and persist throughout the shaking event on level ground. The dilation spikes on the mid slope or on the sloping ground are substantial and basically reach the maximum recording value possible throughout the entire shaking event. If we look at this in terms of the response spectra from the base input motion to the different accelerometers up through the top, you can see the input motion is well defined at a period of 1 second, or that's the 1 Hertz input motion. But very clearly, you can see all the other accelerometers are indicating that liquefaction has occurred. In contrast to that, as the soil becomes more well graded, you actually see 2 things occurring. You see the period being extended slightly, but you see the amplitude increasing, the spectral accelerations going up due to the strong dilative nature of the material. And so it's a very, very different type of process. This one, even though it may be liquefying in terms of a pore pressure type of signature, has retained its stiffness throughout the shaking event. Again, we can look at the response in terms of pore pressures, and you can see on the left-hand side, you can see the pore pressures for the level ground case, as well as for the sloping ground case. And we reach an RU of 1 almost immediately within the first cycle, and that is maintained even after shaking. And then we have a gradual decay in the pore pressure. And the same thing happens at both elevations. On mid slope, we also reach an RU of 1. It decays slightly. That's due to the static stress components on the slope. But then we also have gradual dissipation in time, taking almost 400 seconds. In contrast to that, jumping to the bottom right, you can see it's a couple more cycles before pore pressures are reached. And on top of that, as soon as shaking is over, we immediately start to see dissipation of the pore pressures more rapidly. And basically pore pressures have fully dissipated at a time of about 100 seconds. That's about 1/4 of the time for the well-graded soil compared to the poorly graded soil. And it's even more amplified on the sloping ground conditions. And the other 2 soils are kind of filling in the spectrum in between.
2 minutes left.
Okay. You can also see it in terms of the stress strain behavior. And so you see a fully liquefied stress strain condition in the upper left for the 100A material. And this is on the upper bench. And you can see that in the well-graded materials, you start to see these dilation spikes at the limits of cycling. That's reflecting the more dilative nature of the material. On the sloping ground, you can now see the static bias in the downward direction. You can see the total strain is about plus or minus 4%, but you can see the strong some dilation spikes for the 100A. And that the strength of the dilation and the resistance to downslope movement is certainly amplified and much stronger as the soil becomes more well graded. And you can see that in the bottom plots. You can see the strong negative dilation spikes in the excess pore pressure profile as well. So that's the dynamic response extracted from the accelerations and the pore pressure transducers. We also have the permanent deformations as well. I'll quickly show you this video, but notice I've just because of formatting, I've rearranged things a little bit. So the 100A model is down here. The 12 CU model is in the upper right. But if we get this going here, you can start to see the deformations through the shaking. And you can see the 100A model on the bottom left relative to the 12 CU model on the top right, the magnitude of deformations throughout the slope are substantially larger, on the order of a factor of 4. And these are just now in the correct positions again, the final deformations for those 4 different soils. And so this is something that we need to be able to predict and to be able to actually capture in practice. The upper left is referenced, really exemplifies what is kind of standard of practice in many ways for industry. Whereas in the bottom right, this is more of what we believe the performance to be of well-graded soils in the field. And so to conclude and wrap up, there's a number of points here regarding what happens as CU increases. First of all, from an index perspective, the void ratio decreases, the permeability decreases, and the shear modulus increases. The cone tip resistance goes up substantially with CU, and this actually could lead to a whole nother conversation regarding penetration resistance and what should be expected in a well-graded gravelly material. Well-graded soils can maintain their stiffness throughout liquefaction, even when you reach an RU of 1. And so that may not be an appropriate definition or a useful definition for predicting deformations. Higher CU soils have greater resistance to generation and faster dissipation of pore pressures. On the slope, higher CU soils exhibit strong dilation and display substantially less than poorly graded soils. And all this is to say relative density alone is not sufficient. We need to be capturing other parameters. And so the broader ongoing work includes more centrifuge testing, laboratory triaxial and DSS testing, discrete element modeling to map fabric changes to cyclic behavior, as well as flak modeling with PM4 sand, and being very careful on how we calibrate that to capture some of these unique effects as well. So with that, happy to answer questions. Here's part of the research group. All this work was performed during the pandemic under COVID conditions, which led to a little bit of additional challenges, but they did a great job with it. So with that, happy to pass it back over to you. Thank you.